Application of the $N$TH term in real-world contexts. Welcome, everyone. In our previous lessons, we spent a lot of time working with the algebra behind the arithmetic progression formula, practicing how to rearrange terms and solve for unknown variables. But today, we are moving beyond just moving numbers around on a page. The real power and true utility of the nth term formula, which is a sub n equals a plus open parenthesis n minus 1 close parenthesis d, is its ability to model what is actually happening in the real world. You'll see that any situation where a quantity increases or decreases by a constant amount over equal intervals of time or space can be represented as an arithmetic progression. Over the next few slides, I will show you exactly how to identify these patterns in finance and physical arrangements, so you can apply this formula to solve practical problems. Modeling real-world problems. Now that we understand that the nth term formula is a powerful tool for modeling real-world scenarios, let's discuss how we actually use it. You might look at a word problem and feel a bit overwhelmed by all the text, but the secret is to follow a systematic process. Our goal here is to translate those words into a mathematical equation. First, you need to identify the sequence. Before you start grabbing numbers, ask yourself, is this situation describing a constant increase or a constant decrease? This tells you immediately if you are dealing with an arithmetic progression. Second, you need to extract the first term, which we represent with the letter A. Look closely at the problem to find the starting value of the sequence. Third, you must determine the common difference, represented by the letter T. This is the constant amount being added or subtracted in each step. Now, pay close attention here. If the problem describes a decrease or a decay, you must remember that D will be a negative value. Fourth, you need to define the position, which we call N. This is simply identifying which specific term or which specific time period the question is asking you about. Finally, once you have all your pieces, you apply the formula. You will substitute your values for A, D, and N into the formula, which is a sub n equals a plus n minus 1 times d. By doing this, you can calculate the required value, which is the nth term. In the next few slides, we are going to walk through two practical examples to see this exact process in action. Example 1, Financial Growth, Simple Interest. Now that we understand the systematic process of identifying our variables, let's put that theory into practice with our first real-world example. We are going to look at financial growth, specifically through the lens of simple interest. You might wonder why simple interest is relevant to our topic. Well, it is a classic example of an arithmetic progression. This is because, with simple interest, the interest is calculated only on the original principal amount, the initial money you put in. Because that starting amount never changes, the actual dollar amount of interest added to your account every single year remains constant. Whenever you see a constant amount being added, you know you are dealing with an arithmetic progression. Let's look at the specific scenario presented here. Imagine a student deposits $10,000 into a savings account. This account pays a simple interest rate of 5% per annum, which just means 5% per year. Our goal is to use the arithmetic progression formula to determine the total amount of money that will be in the account at the end of the 12th year. As we move to the next slide, we will break this down step by step to identify our first term and our common difference. Example 1, Financial Growth, Simple Interest, Step-by-Step Solution. First, we need to calculate the annual interest. To do this, we use the simple interest formula, P times R times T, all divided by 100. Plugging in our values, that is 10,000 times 5 times 1 divided by 100, which gives us $500. This represents the fixed amount of money added to the account every single year. Next, we move to step 2, where we identify our first term, which we call A. It is important to remember that the first term in our sequence represents the total amount in the account at the end of the first year. So, we take our original principal of $10,000 and add that first year of interest we just calculated, which is $500. This gives us a first term, of $10,500. Finally, in step 3, we identify the common difference, represented by the letter D. Since this is simple interest, the amount of interest added remains constant every year. Therefore, our common difference, D, is simply that $500 we calculated in the first step. Now that we have established our scenario in the previous slide, where we are looking at a $10,000 deposit with 5% simple interest, let's walk through the first 3 steps of our solution. Now that we have identified E and D, we will move to the next slide to determine our N value and complete the calculation. Example 1, Financial Growth Simple Interest, Step-by-Step Solution. Step 4 is all about identifying the position or the term number that we are looking for. In our scenario, the problem asks us for the total amount in the account at the end of the 12th year. Therefore, our N equals 12. Finally, in step 5, we apply everything we have gathered into our nth term formula. We start with a sub-12, which represents the amount at the 12th year. This is equal to our first term, A plus the quantity of n minus 1, all multiplied by the common difference. D substituting our specific values, we have a sub-12 equals 10,500 plus the quantity of 12 minus 1, multiplied by 500. When we simplify the parentheses, 12 minus 1 gives us 11. So, we are left with 10,500 plus 11 times 500. Calculating 11 times 500 gives us 5,500. When we add that to our initial amount of 10,500, we arrive at our final result, $16,000. Now that we have identified our starting amount and our annual increase from the previous steps, let's move on to the final stages of our calculation. This brings us to our conclusion in the next slide, where we can clearly state the total savings after 12 years. Example 1, Financial Growth Simple Interest, Conclusion. So, to wrap up our first example, we can clearly see our final result. After performing all the calculations, we conclude that the total amount in the savings account at the end of the 12th year will be $16,000. This shows how we can use the nth term formula to predict long-term financial growth without having to calculate every single year individually. Now, let's shift our focus from finance to a different type of scenario, looking at how arithmetic progressions can model physical arrangements. Example 2. Physical arrangements, linear decay. Now that we have seen how the nth term formula works for financial growth, let's shift our focus to a different type of application, physical arrangements. Arithmetic progressions are incredibly useful when we need to calculate the number of items in structured patterns, such as the number of seats in a stadium, or, as we will see in our next example, the arrangement of plants in a garden. Let's look at this specific scenario. Imagine a gardener is designing a triangular flower bed. The design starts with the first row, at the very top, containing 15 flowers. As the rows progress downwards, each subsequent row increases by exactly 3 more flowers than the row immediately before it. Our task here is to determine the total number of flowers that will be present in the 20th row. As we move to the next slide, we will break this down step by step to identify our variables. Example 2, Physical Arrangements, Linear Decay, Step-by-Step Solution. First, we need to identify our first term, which we represent with the letter E. Looking back at our problem description, the very first row at the top of the garden contains 15 flowers. Therefore, our first term, equals 15. Next, we move to step 2, where we identify the common difference, represented by the letter D. The problem states that each subsequent row increases by 3 flowers. Since this is a constant increase, our common difference, D, is positive 3. Now that we have set up our scenario involving the triangular flower bed, let's move into the actual calculation. We'll break this down into the first 2 essential steps. With these 2 values identified, we are now ready to move on to the next slide to determine which specific row we are targeting. Example 2, Physical Arrangements, Linear Decay, Step-by-Step Solution. Step 3 is to identify the position, which we represent with the letter N in our gardening scenario, the question specifically asks us how many flowers will be in the 20th row. Therefore, our N equals 20. Finally, we reach step 4, where we apply the nth term formula that we've been using throughout this lesson. We start by writing out the formula for the 20th term, which is a sub 20. This is equal to a plus the quantity of 20 minus 1, all multiplied by d. Now, let's substitute the values we identified earlier. We replace a with 15 and d with 3. This gives us 15 plus the quantity of 19 multiplied by 3. When we perform that multiplication, 19 times 3, we get 57. So, our equation simplifies to 15 plus 57. Now that we have identified our starting value and our common difference from the previous slide, let's move on to the final steps of our calculation. In the next slide, we will perform that final addition to find our total number of flowers. Example 2, Physical Arrangements, Linear Decay, Conclusion. So, to wrap up our second example, we can see that by applying the formula, we arrived at our final result. Therefore, our conclusion is that there are 72 flowers in the 20th row. This completes our calculation for the flower bed arrangement. Now, before we move on to the final summary, let's take a moment to look at some common pitfalls that students often encounter when solving these types of problems. Common mistakes to avoid. First, a very frequent error is confusing n with a sub n. It sounds similar, but they represent completely different things. Think of n as the which one, it is the position or the rank, like saying the 10th row. On the other hand, a sub n is the how many, it is the actual value or the quantity, such as 50 flowers. Always double-check if the question is asking for the position or the value itself. Second, be very careful with the sign of our common difference. In our previous examples, like the flower bed, the number of flowers was increasing, so d was positive. However, if you encounter a problem involving decay or a decrease, for instance, if a problem states that each row has 2 fewer plants, you must remember to make d negative. In that case, d would be negative 2. If you forget that negative sign, your entire calculation will move in the wrong direction. Finally, watch out for misidentifying the first term. This can be tricky. Sometimes, a problem will give you a starting value at time 0. But remember, in an arithmetic progression, the first term, a, usually refers to the value after the first interval has actually passed. Always read the wording of the problem very carefully to determine if the value provided is a sub 0 or a sub 1. Taking that extra second to clarify your starting point will save you a lot of trouble later on. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that lead to the wrong answer. Let's look at 3 specific mistakes to watch out for. Key takeaways. All right, we have reached the end of our lesson. Before you head off, let's quickly recap the key takeaways from today's session to ensure you have a solid grasp of how to apply the nth term formula to the real world. First, let's talk about linearity. The most important thing to look for in a word problem is a constant rate of change. If you see a situation where something increases or decreases by the exact same amount every single time, just like we saw with the simple interest in our first example and the flower rows in our second, then you are looking at an arithmetic progression. Second, think about the power of formula application. The beauty of the formula, a sub n equals a plus, n minus 1, times d, is that it acts like a mathematical time machine. Instead of manually writing out a long list of numbers and adding them up one by one, which is where most mistakes happen, this formula allows you to jump straight to any future value or position you need to find. Finally, I want you to remember this variable mapping. When you approach a new problem, your first task is to map the words in the story to the variables in our formula. Think of A as your starting point, or your initial value and first observation. D represents your constant rate of change. Just a reminder from our discussion on common mistakes. If the value is growing, D is positive, but if the value is decaying or decreasing, D must be negative. N is simply the position or the specific time period you are interested in, the which one part of the problem. And lastly, a sub n is your result. It is the final value or the how many at that specific position. If you can master this mapping, you can solve almost any linear word problem. Great job today!